A big application for integral for calculus is physics. So for section 2.5, we're going to talk about some physical applications. So we have one example that this one is talking about a tent with inverted circular cone with a height is 10 meter from the top to bottom, and then the base radius is 4 meter. It is filled with water to a height of 8 meter. Find the work required to empty the tank by pumping all of the water to the to the top of the tank. So this is a work-related physics problem. So in here we will have some informations or pre-knowledge we need to know, which is the work equals to the force multiplied by the height. And we also have uh, or work equal to force times the distance. For this case, is the height. And we also have the mass of something is going to be the density times the volume. And of course, our force is going to be related to the mass. So here I started with an inverted circular cone where we know that the height from the top all the way to the bottom is 10 meter, but we only filled it up to 8 meters for the water. The radius of the base is 4. Because it's inverted, so the base is actually on the top. And that is all the numbers we have. So we want to find the force to pumping up, the work to pumping up all the water. So the water is going to pumping from the bottom to the top. So at the beginning, we will have less work to do versus all the way to the end, we will have more work to do because it's more distance. So we will use the triangles or similar triangles as the relations to talk about those. So the concept is still, we are going to slice the water, in particularly those things. We're going to slice them. And in one slice, we'll have a distance of delta x. In the future, is going to be our dx. They will have a radius, which is a mystery radius. We're not sure what is that radius. And then this one also going to separate the distance from the top to this layers and from this layer to the bottom. Say if this is going to be the x, then the bottom is going to be 10 minus x because the total is going to be 10. And from this way to set it up, we are able to draw a right triangle or a similar triangle in particularly. Where the top is the top radius 4 and then a new radius r and then a 10 minus x versus a 10. And from this one, we can find the relation for the radius r using the similar triangles, where r over 10 minus x equals to 4 over 10. In other words, r is equals to 2/5 times 10 minus x. Then once we know the r using the x to representing it, we also know this slice, it is filled with water. So that means we will have a volume. So the volume for this slice is going to be the pi r squared multiplied by the distance or the height, which is the base of the area multiplied by the height. That's the volume. Again, this is a circular kind of cylinder shape. So we're using the pi r squared for the circle area. So for this case, plug in the r, which is going to be 4 pi over 25 times 10 minus x squared delta x. And this is the volume. But we want to talk about work. So in order for us to talk about work, I do not need volume, I need force. And then in order for us to talk about force, I need mass. I have the volume, so the mass of the water is going to be the density multiplied by the volume. The density is 1,000 kilogram per meter cube. So we will have the 1,000 multiplied by the 4 pi over 25, 10 minus x squared delta x, which is going to be 160 pi 10 minus x squared delta x. Okay, again, everything we're doing here, we're just talking about this one slice. So once I have the mass, now I finally can talk about the force. So the force is going to be the mass multiplied by the gravity, which is 9.8. So 9.8 multiplied by the 160 pi times 10 minus x squared delta x, which we end up with 1568 pi times 10 minus x squared delta x. And finally, the force, the work for us to lifting this slice up is going to be the full force multiplied by the height. The distance. The distance is going to be the distance. The distance, I'm using this color, is going to be the distance this piece of water is going to travel out, which is going to be this one. So the force 1568 pi times 10 minus x squared delta x, we need to multiply by another x. And this is the force we need to do to lifting one slice of the water out from this circular cone shape. Now we need to do the same thing for every single one of them. But this is the general form. So what we need to do is we're going to do the same thing for each side and adding up all the force. So that is the total force. So the total work is going to be the summations of all. So it's going to be integrating from 2 to 10. Where are the 2 and 10 coming from? That is going to be the distance from the lowest distance, which is only need to travel 2 units because this is 8, this is 10. So by only traveling 2 meters in terms of distance all the way to, they need to travel 10 distance. So that's why it's 2 to 10 of all the works 1568 pi times the x, which is this x here, times 10 minus x squared. I still this square is outside. Delta x, which is rewrite as dx. So that's why I need to move this x to the front. Let me change the color so you can see where the x is coming from. And then delta x is going to rewrite as dx. This is the setup. Now we're going to move on to our calculation. Move the constant out. Multiply the 10 minus x squared, which is 100, minus 20x plus x squared dx, which is 100x minus 20x squared plus x cubed. This is an easy one to find the antiderivative. Times 100 over 2 x squared minus 20 over 3 x cubed plus x4 over 4, integrating from 2 to 10, which is going to be 1568 pi. 100 times another 100 over 2 minus 20 times 1,000 over 3 plus 1 with 4 zeros over 4 minus 100 times 4 over 2 plus 20 times 8 over 3 minus 16 over 4. So using the calculator, we ended up with 1568 pi times 2048 over 3. Because this is a word problem, we're going to punch into the calculator. We got approximately 3.4 times 10 to the 6th power. Because this is the work, so we're going to using the J, which is the, I believe is joule, as the unit for the work. And this is the problem for this physics. So we first need to set up graphing it to know what we're doing. And then because it's a calculus class, so we're only focusing on one slice. And then for this one slice, the width of the slice is always going to be dx or dy, depending on how you slice them. And then we're going to try our best to find some relations. We can rewriting all the unknown variables. For this case, the unknown variable is the r here, the aperture radius for the slice. Then we can using the similar triangles to build up a relations between the r and the x. This x is corresponding to this x, and this x is going to range. So if you want, you can write it as, say, xi to separate it with the traditional x. But for me, I can figure out, I can separating them, so I just keep it as x, because in the futures, when we actually set it up, we're still going to using x instead of xi. And this x, which is corresponding to the distance the water is going to travel, is going to range from a 2 all the way to a 10. So that's why we set it up from the 2 to 10. There's a lot of physics kind of pre-knowledge is required for all those physics, or for all those application problems. Here, in order for us to find the force work, we need to find the force. In order for us to find the force, we need to find the mass. In order to find the mass, we need to find the volume. In order to find the volumes, that's how we set up everything. So the way to think about any of the problem, we normally do from backwards. And then when we figure out what we need, it's going to more doing on the forward directions.